Okay. Hello, everyone, and welcome to the Latin American webinars on physics. My name is Joel Jones from the PUCP in Peru, and I will be your host today. This is webinar number 52, and we're having Nancy Wandkowsky as a speaker. She's a postdoc at the University of Madison, Wisconsin, and more specifically at WIPAC, the Wisconsin IceCube Particle Astrophysics Center. Right, so Nancy finished her PhD on the Karlsruhe Institute of Technology, where she worked at the Catherine experiment. But she's been a postdoc at IceCube since 2014 and has worked on astrophysical neutrinos. So today, Nancy will be talking about the high energy astrophysical neutrinos, and we're very glad to have her as our speaker today. Before we begin, let me remind you that you can also be part of the discussion by writing questions and comments on the YouTube live chat system, right, which should be on the right side of your screen. So now I'll hand you over to Nancy. Okay, so please go ahead whenever you're ready.
Thank you very much for the nice introduction and for actually giving me the opportunity to talk to you about astrophysical neutrinos. Let me try to share that screen. Can you see the slides in full screen?
Yes.
Okay, perfect. Okay.
Oh,
so,
not anymore. I could see them, not anymore.
Interesting.
So are you sharing your screen?
I am. Start screen share.
Okay, now I can see it.
Yeah.
And now I see you.
Why does it go away? So apparently once I go to full screen with the screen share.
Mm-hmm.
Maybe we can switch off your camera.
Say again?
Try to switch off your camera.
Oh, that could work. I can do that for you.
How do I do that?
I switched you off right now. Okay, let's see. No, that
Does it
didn't
work?
work. No. I am switching it back on.
Okay.
Nancy, maybe you can try to share the screen, the full desktop, because maybe you're just sharing the PowerPoint window.
So usually what works for me.
Okay, yeah, let me try.
Okay, go ahead. Yes.
Does that seem okay?
That's
okay,
perfect.
Then it was the problem with just trying to share the PowerPoint. Okay, so after these issues, let me give a short overview. So I will firstly, obviously, introduce a little bit about astrophysical neutrinos and IceCube before I will then come to the main topic, which is the high energy starting events, a selection that basically gave us the first detection of astrophysical neutrinos. And then I will talk a bit about our basically latest hot topic, which is our multi-messenger approach to actually finding the sources of astrophysical neutrinos. Okay. So why do we actually expect astrophysical neutrinos to exist? Well, we know that that cosmic rays exist. So they consist mainly of protons. And if those protons interact with the interstellar medium, you expect to have a vast production of pions. And from those, you actually expect to get neutrinos. So you expect a tight coupling between those cosmic ray protons and the neutrinos. So we have measured the cosmic ray spectrum very well. We have mapped some of its features like the knee and the ankle, and we know that at some point there is a switch from a galactic contribution to an extragalactic contribution. And although we know so much already about the cosmic rays, we don't actually really know the sources in detail and the mechanisms that's actually driving them. So we want to utilize the neutrinos to actually learn more about those mechanisms. And what I forgot to say is that the nice thing about neutrinos is that they are not affected by the magnetic fields in the universe. So they actually point straight back to their source. So that's a nice feature about them. And basically the two most prominent sources for neutrinos are the active galactic nuclei, where you have the relativistic jet coming from the central engine, most likely a black hole in galaxies, and which produce a continuous emission of neutrinos. And furthermore, you can have gamma ray bursts, where the current model is like a relativistically expanding fireball or jet, and those are neutrino sources of transient nature because of the spinning of the particular source. So both of these mechanisms can lead to neutrino production, and are the models that we are currently testing. So in order to detect neutrinos, because of their low rate of interaction, you actually need a really huge detector. In case of IceCube, this is a 1 cubic kilometer volume of clear Antarctic ice, which is instrumented with about 5,000 digital optical modules on a total of 86 strings, which are recording the light produced by neutrino interactions. I'll come to that in a second. So these strings have, the DOMs on these strings have a vertical spacing of about 70 meters, and the inter-string spacing is about 125 meters. The full detector was completed in 2010, so since now 7 years we are taking data in full detector operation, but even before that we already took data in with the partial detector. So let me see if that works. So here's a nice video of what happens in the detector. So you have a neutrino incoming, interacting with one of the ice molecules and producing secondary particles. In this case, it's a muon is being produced, and this muon travels faster than the speed of light in the ice, and hence emits Cherenkov light, or leads to the emission of Cherenkov light. And this blue light is what we actually detect with our sensors in the ice. So you see each of these colored blobs is one sensor that actually recorded a hit. And the color scale gives you a timing information, which basically you can use to get a sense of the direction the event came from. And the size of the colored blobs gives you a sense of how much charge was recorded, which is proportional to the energy deposition at this position in the detector. So that's the information that we can use to learn something about the neutrino that actually produced this event. So there's 3 types of events of neutrino signatures that we expect in the detector. The one that we just saw was a charged current muon neutrino interacting and producing a secondary muon, which leaves a long track in the detector. So the stochastics can be the stochastic lead to either homogeneous emission or sometimes also very inhomogeneous emission. So you can also see stretches without deposited light in between. But this one is a nice muon track that you see here. And due to the fact that this muon can actually leave the detector, or the interaction can actually happen before the detector and the muon then only enters the detector, you don't have such good information about the energy. So our average energy resolution is only about a factor of 2. But due to the long lever arm of this track, you have a very good angular resolution. So we can pinpoint the event very, very well, which is great for point sources, of course, or for finding point sources. Then the second type of event, which is actually the main event for today's talk, is what we call a cascade event, which is either any neutral current interaction or any interaction of an electron neutrino in the detector. And here, basically, due to the fact that you you have electrons which don't travel very far, or you have the neutral current interaction where you have local hadronic processes, you get a very localized event energy deposition. That means that all of the energy of your event is ideally contained within the detector, so you have a very, very good energy resolution of about 15%. Unfortunately, though, since we are in this case missing the lever arm, the angular resolution is relatively bad. So it's still decent, 10 to 15 degrees, depending on the energies, but it's by far not as good as for the tracks. And then the third signature, which we actually still need to find, is the signature of a charged current tau neutrino interaction, where you basically first have the interaction of the neutrino producing the lepton, the tau lepton, and then subsequently you have the decay of this tau lepton. And the thing is that these two processes produce you cascade-like event signatures, but in order to be able to separate those, you need a very high energy incident neutrino. So the average tau decay length is about 50 meter per PeV, and since we have this 125 meter string spacing, you actually need pretty high energy new taus to produce a signature which you can actually distinguish from a single cascade. So we are still searching very hard for that, but so far we haven't found it. So how do we actually isolate those neutrino events from the vast backgrounds of atmospheric muons that are incident on our detector all the time? There's two main strategies. The one is shown on the left, which are upgoing tracks, where you basically remove all the muon background, because you're only looking at those neutrinos that actually travel through the Earth, and any muon that would attempt to travel there would obviously be absorbed. So you don't have you don't have to deal with the atmospheric muon background. And the effective volume for this is actually pretty large, because, as I said, the neutrinos can interact outside of the detector and the muon can still make it into the detector. However, this selection is only sensitive to muon neutrinos and to the northern sky. So in order to get neutrinos from the whole sky, we implemented a second method, which is utilizing a veto to get rid of the atmospheric muons. So in this case, you can actually also look at the southern sky. However, since you require that your event has to be deep inside the detector, you actually have a smaller effective volume. So let me talk a little bit more about this active veto technique, which is what we use in the high energy starting event analysis. So on the left sketch, you can see the orange region is what we actually is the veto region that we define. So what that means is that we actually look for hints of an incoming muon in this region. So a muon that comes from outside and is of decently high energy has a very high chance of actually depositing energy there. While if you look at neutrino interactions that happen inside the detector, there would be no trace of this event in this outer layer region. And at the same time, we can use this technique to get a better handle on our remaining atmospheric muon background. So for that, we actually define a second veto layer inside of the outer veto layer, where we basically check if we find events that deposit light in the outer veto layer, so hinting towards actually having that this is an incoming muon, but no hits in this inner veto layer. So because of the stochastic nature of the muons, this can actually happen. So you try to infer from observing this type of events that don't deposit light in this second veto layer, you try to infer of how probable it is that an incoming muon can actually sneak through your real veto layer. another very nice thing that nature gave us here is that we have what we call the atmospheric neutrino self-veto. So what you have here is basically you have your atmospheric neutrinos which are produced in the cosmic ray air showers, and those neutrinos obviously in the same air showers you have a lot of atmospheric muons produced. So these muons accompany your neutrino. In the case of a muon neutrino, you have a very tight coupling with a correlated muon. In case of electron neutrinos, you only have the uncorrelated muons. But anyway, there is a high chance that the muon deposits light in your outer veto layer, and by that you actually remove the atmospheric neutrino from your sample. So, and how we parameterize that, or how we deal with that, is that we actually we have simulations of atmospheric neutrinos for our detector, and we correct their detection probability according to this process. So we performed Corsica simulations to obtain a parameterization, where you can find the references to here, perform Corsica simulations to get this parameterization of energy and zenith dependence. And by that, we basically correct the neutrino detection with this, what we call self-veto probability. And yeah, that means that, so on the right, you can see the spectrum, or actually the number of neutrinos that you would expect as a function of cosine zenith or cosine declination. And you see that this self-veto results in a reduction of atmospheric neutrinos in the southern sky. So there you would expect then yeah, to find less atmospheric neutrinos, and the astrophysical neutrinos clearly sticking out. So here's what I just said. It's how we parameterize it. So the crosses are the Corsica simulation, and the solid lines are the parameterizations that we actually use in the in our correction. And we are currently working on an updated version of this using so this used Sybil 2.1, which had no charm in there, but the new version of Sybil 2.3 has charm, so we are working on updating that currently. Okay, so with 2 years of data, we basically were able to show that astrophysical neutrinos exist. By now we have collected even more. Well, we have now collected 7 years, but this the latest analysis was about 6 years of data, where in total we observed 80 events. And in this full sample, you expect about 15.6 atmospheric neutrinos and about 25 atmospheric muons. And in the plot, you can see the all these events in our observables, which is the deposited energy in the detector and the direction the event came from. So we still can't find any sign of prompt in our data. And one thing that we changed, and which is important if people are trying to reproduce our results, is that we are actually now using a more correct cross-section model, which predicts a about 15% different flux. So since the atmospheric muons are mainly populated at the very low energies, we actually only fit in a region above 60 TeV deposited. So that leaves us with about 50 events. And you can see that here, the background, in this region, the background gets drastically reduced, and you only have an expectation of about 1 atmospheric or a little more atmospheric muons. So what does the spectrum look like? So on the left, you can see the distribution in energy. So you see that we get rid of most of the muons in red, and we have a clear excess above the conventional atmospheric neutrino expectation. And on the right, you can nicely see the suppression in the northern sky due to the absorption in the Earth. And you can see in the southern sky that we have this suppression of atmospheric neutrinos due to the self-veto and the clear excess above that expectation, which we attribute to astrophysical neutrinos. So by now we have the background-only hypothesis can be rejected with 8 sigma. So yeah, pretty significant. However, so one thing that is interesting, that with each additional data sample that we added, or with each additional data that we added to the sample, the spectral index got softer and softer. So we started off with something like 2.3, and this latest iteration gave us 2.9, which is a really soft spectrum. So how does this fit in with the other analysis? So I told you before that we have this other method where we are looking for outgoing neutrinos, outgoing muon neutrinos, and their latest, so they are using by now 8 years of data. So they are using some of the non-complete detector configurations, and they obtain a relatively hard spectral index of 2.19. So if you look at this in a combined plot, so the pink is this outgoing muon neutrinos, and the black is our starting events 6-year analysis, you can see that there is a tension of about, in this case, it's about 2.3 sigma. So in the end, we think that that we are observing the same neutrinos. So the question is, where could this ever-increasing tension come from? And of course, it's it's a little hard to say, because we are not looking at the same events here. So one is outgoing neutrinos, and one is all sky neutrinos dominated by actually electron-neutrino interaction. So what we tried in our 6-year analysis is actually looking into more complicated models than just a single power law. So the next extension that you can do is actually assuming a 2-component power law, so a dual power law. And if we just fit for a dual power law with just the starting event data, the fit definitely prefers a single power law. So what we did is that we actually introduced a prior to one of the components, which is in this case obviously the this outgoing muon neutrino spectrum. So these the orange contours here show you the results of this dual power law fit, where we use the pink contour as a prior for the orange contour with the downgoing triangle. So you can see that the fit pulls it towards softer spectra, which is somewhat expected, and that especially the contour of the second, much softer component is very, very large. So it's absolutely not conclusive with the small number of events that we have in the starting event sample. But since we have this small tension, we have to look at possibilities of more complicated models. So as I said, there is some inherent differences between the data sets. So our starting events are mostly cascades, while the other analysis are tracks only, so nu E versus nu mu. The starting events are dominated by the downgoing portion, where we or by the southern sky portion, where we actually have the galactic center, and the other analysis looking at upgoing only. So we tried to basically look at upgoing versus downgoing within the starting event sample, or cascade versus tracks, but unfortunately we cannot do the nice combination of upgoing plus tracks, because we have basically no events left if we choose this combination. So that would be the most fair comparison to the upgoing muon neutrinos, but unfortunately our statistics in the starting event sample for that is too small. However, if we look at these other splits, we can't really resolve the tension. So we are currently working on a new analysis that actually combines the different data samples in one likelihood analysis, which will give us a much better handle on this. Okay, so if we assume that whatever we measure with the starting events defines your astrophysical neutrinos, so an e⁻².9 spectrum, then the first thing is that you would not expect a glacial resonance event with this soft spectrum. So the fact that we haven't seen that in the starting event sample would not be surprising. And you can say a few more things about the production mechanism of these neutrinos. So if you look at the ultra-high energy cosmic ray accelerators, we know from measurements of Auger and others that we find energies above 10⁻⁵ electron volts, and that if you think that Fermi shock acceleration is the mechanism that actually produces these high energy cosmic rays, this would imply a spectral index of about 2 and not higher, not softer than 2.2. So if your neutrinos are mainly produced by PP interaction, that would mean that there would be a strong coupling between the spectrum of the neutrino and the spectrum of the proton. So that would mean that you would expect a neutrino spectrum of not softer than e⁻².2, which is clearly not what we see with the starting events. It's still compatible with what we see with the muon neutrinos, however. If you allow proton-gamma interaction, then, however, the neutrino spectrum is not coupled to the proton spectrum anymore, because also the photons that your protons interact with matter here. So in this case, you can produce much softer spectra. So we can make some restrictions here with our data. And so we have looked at 6 years of data now, but as you know, data is coming in every minute, and we are currently working on a 7.5-year data set. And obviously, we want to also improve our methods. And one area where we want to improve are the reconstruction of these events, because especially if you look at point sources, you want to make sure that you're actually pinpointing your events reliably. So the reconstructions rely on the correct modeling of the South Pole ice. And in the simplest model, or in the model that we used so far, we actually have not considered the fact that the South Pole ice actually shows an anisotropy and the tilt. What does that mean? So if you're looking on the right plot, it's a sketch of the detector. So all the numbers correspond to the different strings that are installed in the ice. And due to the shear of the ice layers and the shear of the ice layers, what you actually have is that in one direction, you actually have an enhanced scattering, while in the orthogonal region, you have a decreased scattering of the photons there. And that, in the end, leads to an anisotropy in your observed pattern of light. So, and if you do not take this into account, you're actually making a wrong assumption, obviously, about what you would actually see. And this became especially important for our recent search for new taus, because here, as I told you, we are looking for the signature of the two cascades, so this double bang. And if you neglect the anisotropy, then actually a single cascade can be misidentified as a double cascade. Because you're separating the single cascade into two events if you do not account for this enhanced scattering in one direction. So for this reason, we have implemented the anisotropy in our reconstructions, and here is basically a likelihood map of our old reconstruction, which does not use the anisotropy information. And what we do basically for our reconstructions for the Hezi events is that we produce we scan the entire sky. So we assume a heel-pix map over the sky with a very fine grid, and we fit for the particular pixel, so for the particular direction, and record the likelihoods that the event could have actually come from that direction. And that's the map that you see here, the all the different likelihoods, and you get a corresponding best fit position and an uncertainty. And if you now switch these reconstructions that do not contain the anisotropy to the new reconstruction that actually has the anisotropy information, you can get a very significant shift of your best fit, even outside the old error contours. So we are currently verifying that all of these improvements are actually doing what we think they are doing, but this could produce a significant shift of some of our previously released events, which obviously can have implications especially for the point sources that we are trying to find with these events. Okay, so as I said, we are currently working on the about 7.5-year data set. We obviously want to use improved reconstructions. We also, in the last year, we have undertaken a large effort to recalibrate our historic data. So we know by now that our calibration has not been entirely correct previously. And effectively, this means that we have to down correct all the charges and hence also the energies by about 4%. So it's not a big effect, but something that will affect the energies that we previously released. And as I said, there is a slight tension with the upgoing neutrino analysis, and this, of course, raises the question if the single power law is still the best fit description of the data set. So we want to test different models, obviously, the dual power law as the next extension. Then we're also looking into models like the log paraboloid power law, which is basically which is many power laws with different spectral indices. And there's obviously also the possibility that we have something else than just astrophysical neutrinos in our data, for example, dark matter from decay or annihilation in the galactic center. And there is obviously always the exciting possibility of finding new physics in the data, which we'll be handling via effective operators. And since this HESI or high energy starting event sample was in the beginning not aimed at making detailed yielding a detailed understanding of the astrophysical spectrum, but it was just aimed at actually discovering astrophysical neutrinos, we neglected some of the systematics that at the time when we had the very low statistics actually didn't matter. But by now we collected so much more data that we also have to take into account additional systematics, like, for example, the pi-k ratio. We previously only used 1 atmospheric flux in our fits and didn't give it much variability beyond just the normalization and some more. And if we now add systematics, and we are also looking at more complicated models than just the dual power law, we are obviously introducing a larger number of parameters, and that actually for that to be able to handle that, we actually need to utilize a Bayesian approach now beyond what we did before. So Wilks doesn't necessarily hold anymore. And for this, we're actually planning a publication for 2018, spring 2018. Okay, in the last few minutes, let me talk a little bit about our latest hot topic in IceCube, which is multi-messenger physics with multi-messenger physics. So coming back to this picture that we had in the beginning, we we know that, or we would expect that the neutrinos and the cosmic rays have a common source, obviously. So our best chance of finding these the common sources are actually looking at both signals at the same time. So either the photons or the cosmic rays. So what we have set up is this AMON network, so Astrophysical Multi-Messenger Observatory Network, which contains several observatories, so either triggering observatories like IceCube, where you get an event and you send it out to the participating observatories, and they can then follow this event up. So those are the other observatories, the follow-up observatories. And you can see on the lower left a map of what the picture looks like at the moment, or half a year ago. So the main effort here is concentrated at Penn State University. And I want to give two examples. So one is IceCube as a follow-up observatory. So on August 17, 2017, the LIGO-Virgo consortium observed a binary neutron star merger, so the first neutron star merger actually. And the most exciting part of that is that this event was also seen in photons by the Fermi gamma ray burst monitor. So that, of course, so that was basically the first multi-messenger observation of an gravitational wave event, and this triggered us to actually look in our data if we find a coincident neutrino emission. Unfortunately, we haven't found any, but this is a nice example of how we can work together. And there will be more of these events coming in, obviously, from the LIGO-Virgo collaboration. So we are currently setting up a automated follow-up of this type of events. And then you can also have IceCube as a triggering observatory, which we have been running now since about 1.5 years. So what we do is that we are identifying high-energy track-like events. So we are only looking at track-like events to have a good pointing resolution. And we identify them in real time at pole. So we are running our selections at pole. And then if an interesting event is found, so an event that has a high probability of being of astrophysical origin, we send a notice to this this GCN list. So one can subscribe to that to get this information in real time. And there's information like our current reconstructed direction, and this allows other observatories to actually look in this direction to see if they can find a coincident, for example, gamma signal. And this event, then usually it takes about a day for the data to arrive from pole in our data hub. But these events are sent with high priority via satellite, so there is a very small delay until it arrives here, and then an automated process starts that actually refines the position of the event as it was reconstructed at the pole, because there we can't run very computationally intensive reconstructions. So within about 1 hour, we get a very, very good resolution position, which we send as a revision to this GCN list again. So this then results in a resolution of less than 1 square degree usually. So most of the telescopes will then hence be able to observe the 90% uncertainty region. And with some of the observatories like SWIFT, we have special MOUs where we can request them to follow up if we think a signal is or an event is very, very interesting. We can ask them to follow this event up specifically. So there has been a lot of activity going on recently. So you can look at some at them in these astronomer telegrams, where basically the follow-up observatories report their results. So the most interesting one is the upper left, where we reported an event, high energy through going track actually. Which was then followed up by the Fermi-Lat observatory, and they actually detected a flaring source in this region, or in our error region. So we're still crunching the numbers on this event, and you can expect a publication of that pretty soon. But you can, if you look through those lists, you can see that a lot of observatories actually make use of these events and follow up the signals. So this will hopefully lead us to the detection of the sources of astrophysical neutrinos. So let me summarize. So as I said, we have detected the first astrophysical neutrinos, which was already done in November 2013 with 2 years of data. So in summer 2017, we have released our 6-year results, which were shown at ICRC. And in this iteration, we got a very soft spectrum, which is in slight tension with the upgoing mu-neutrino analysis, which of course leads you to considering more complicated models beyond just the single power law. And upcoming, we have a 7.5-year analysis, which utilizes improved reconstructions, other improvements, and more detailed list of actually physics models that we can test now that we have much more statistics than we had in the first iteration of this analysis. And finally, lately, the hot topic, as I said, is finding the point sources via a multi-messenger approach, where we are utilizing this AMON network for. So let me finish with this video. Thank you very much. So you can see here the other telescope, the South Pole telescope, and our ICL, so our IceCube lab in the center, and you can see some nice auroras. So those people that are at the pole with during the winter can enjoy this nice view.
Okay.
What's happening now? I'm getting an infinite.
Whoa.
Yes, you have to stop sharing your screen.
Probably.
It's amazing.
There you go. Thank you very much for the very nice webinar. I think it's the first time a speaker shows us a video. So there you go. So I think it's time for the question round. I don't know if anybody from the audience has got a question. Let's see, hands up. Okay, let me ask a basic question. Mm-hmm. So, okay, first of all, we didn't see any neutrinos coming from this neutron star merger, right? So, what was the chance of actually seeing one? Well, I mean, was that expected not to see any neutrinos? I mean,
so actually, I actually have to be more specific there. So we didn't see any. Actually, we didn't see any neutrinos within a 500-second time window around the time of the merger. So, but then you didn't really. I mean, from the astrophysical background, you did not expect to find anything in this region. So, then, if you actually look at the possible models for neutrino emission for these mergers, you would actually you could have the possibility of finding neutrinos for a period of up to 2 weeks after the event. So we looked in that data sample, and there are some neutrinos in there, but in this case, obviously, you have to consider the background. So we'll actually release a more detailed paper on this in the near future. So you can see the numbers in there. So the paper that I quoted here only basically is talking about the 500-second time window. So the more detailed analysis, you have to be a bit more patient.
Okay, super. So some people here are asking permission for questions. People, you don't have to ask permission. so, okay, let's go. Maybe Mauricio can ask his question.
Yes, I unmuted my microphone. Can you hear me?
Yes.
Okay. Hi, Nancy. Thanks for the talk. So my question is, the recalibration of the DOMs in IceCube, will that also affect things like precision, things like sterile neutrino searches?
So, I mean, it will overall affect the energy spectrum of all of the events. But since it's an overall average shift of 4%, it doesn't actually influence spectral features. So it shifts everything very slightly towards lower energies. But you cannot have basically, it could not have hidden a spectral feature.
Okay, but your resonance would be hit at a different energy, right? For sterile neutrino searches.
Right, but then you have to consider 4%, which is probably much below the resolution that you were using.
Yes, probably so. Yeah, I was just curious about it. Yeah.
I mean, it definitely has to be checked.
Of course. Yeah. Thank you.
Okay.
Yeah, I have a question for Nancy.
Go ahead.
Nancy, first of all, very nice your talk. I wanted to ask you, how many neutrinos are above 1 PeV? Is there more observation about to know what is the trend in that part of the?
You mean in our data samples so far?
Yeah. Yes.
So, I mean, in the from the starting events, we have 3 events above PeV deposited energy. So you always have to be careful if you're talking about PeV neutrino energy or a PeV energy in our detector quantities, because the starting event analysis is measuring deposited energy, and there we have 3 events above PeV. But if you're talking about the muon neutrinos, since we have this large uncertainty of the actual neutrino energy, because the connection between the observed energy of the muon and the neutrino isn't as tight as it is for the starting events. So you have first the event doesn't necessarily have to start in the detector, yada yada. So there it's much harder to say exactly how many events we observed with neutrino energies above PeV. So, but with reconstructed energies, we have this one very, very high energy through-going track. And just recently we had another track which might have above PeV energies, but we haven't finished the analysis on that one either. So that was also one of the alerts that we sent via the GCN, via the AMON network. And then we have a third analysis, which is actually aiming at finding GCK neutrinos, so the very, very, very high energies. And that analysis has found a partially contained event, which is its most probable energy is about 6 PeV. So yeah, there's different samples, and yeah, it's a handful of events, 5, 6.
Okay, so in principle, there is not going to be any surprise in the future, no, with the number of events that, except that it is like an exceptional event. I mean, astrophysical event that you can get a bunch of PeV neutrinos.
I mean, with the current selections that we are using to get these neutrinos, if it continues as it is now, we don't expect to find like a whole bunch of neutrinos. But if there is any event, for example, in the near vicinity that produces high energy neutrinos, like a transient event or something, of course it might happen. But we haven't unblinded the data in some cases, so we actually don't know ourselves.
Yeah. So, and one more question. I mean, no, maybe the other guys can. Yeah.
Camilo also asked permission for a question, so maybe Camilo can go ahead. Are you there, Camilo? Okay. Oh, he's here, but apparently he's having issues with the microphone. He cannot unmute. Let me see if I can. Oh yeah, I cannot unmute you. Yeah, let's see. Okay, maybe while you write down your question, maybe Roberto can finish with his previous question.
Yeah, I was regarding not to the PV neutrino, but in general, what is the status with the determination of the flavors of the different neutrino flavors? I mean, to know if the astrophysical neutrinos likes to be more mu neutrino or tau neutrino or electron.
So as I said, we had this one analysis that was looking to find tau neutrinos within this starting event sample. So that's what I said, where we developed these new reconstruction techniques. And this was not able to find a clear signature of a new tau in the 6-year sample. So we have other methods that are utilizing the waveform information, but most of these samples most of these analyses have not unblinded beyond 2 or 3 years of data. So, and within those we haven't found anything, but we are working on the new iterations that utilize this new recalibrated data and a 6 to 7 year data sample. So there should be coming more analysis of this type in the near future. So let's say within the next half year. But yeah, the latest result was the 6-year starting event search for new taus, and that hasn't found any signature of a new tau, unfortunately.
Okay, thanks. I guess
let me go ahead with Camilo's question.
Thank you, Nancy.
Super. So he asks, what would be the physical interpretation of a model that goes beyond power low energy spectrum? You mentioned this paraboloid scenario. What would produce that?
So that is a model that is motivated by the Blazer spectrum. So I'm unfortunately not really an expert on the on these types of models, but I mean for the double power law, you could imagine something basically two types of sources. So one that produces you a very hard spectrum, like the PP interaction spectrum, and another type of source that is dominated by the photohedronic interaction, so where you can have the softer spectrum of maybe e to the minus 3. And since if you have enough of those sources, then those neutrinos appear both as isotropic, so you can have these two overlapping contributions to your diffuse astrophysical neutrinos, and since this upgoing mu neutrino analysis is only sensitive at very high energies, maybe therefore it's only seeing this part of the sources. So it can't actually see the low energy part for the that's maybe for example produced by the P gamma interactions. So that's why we are looking at these combined data sets to get a better handle on the different systematics, because all these different analyses handle their systematics slightly different and things like that.
So Camilo says thank you.
Yeah, also, thank you.
All right. I don't know if there's any other question. I've seen that on the YouTube. There's a bunch of questions, so maybe we can. If nobody has a question,
I had a very quick question. Actually. So you were talking about really nice talk, by the way, Nancy.
Thank you.
You were talking about this these new models that include the anisotropy because of the ice shear. Does that affect any of the point source searches that have been done?
Oh yeah, definitely. I mean, as I showed in this one example, so this was one of the previously released starting events. And if that turns out to be correct, I mean, it always depends. If basically everything is just shifted and it still stays as diffuse as it is now, then the effect, at least for the diffuse point source searches, is marginal. Because yeah, you're just looking for a diffuse emission. But if you are, for example, trying to, so we have an analysis that is actually using the cascades, where you actually have the biggest effect of this anisotropy on the directional reconstruction. And if you're looking for extended point sources, for example, with those cascades, and suddenly, and you're doing, for example, a catalog search, but your event suddenly gets shifted out of the previously considered error uncertainty, of course, that has a significant effect on this type of point source searches. So it depends a little what kind of search you're looking at.
So are those being updated?
Yes, definitely. I mean, the ones that already use the old data. So we are also planning to do a point source analysis. We just haven't defined in what detail we. I mean, we'll definitely do the diffuse part, but there, as I said, I don't expect too much of a change unless it turns out that there is a systematic shift, that everything shifts towards the horizon or something, or towards the galactic plane. But if it just shifts within the diffuse regime, I don't expect much changes there.
Thanks.
Okay, any other question from the audience? All right, let me have a look at the YouTube chat. Okay, so Herman has got a question. He refers to slide 5. And he is asking, what does the color and size of the spheres mean?
So so the color gives you the timing information. Red means early, green means later hits in time. So you can use that to infer the direction. And the size is proportional to the detected amount of photons, which is which relates to the deposited energy. So in this cascade case, you have this very big blob in the center, which is very close to the interaction vertex, where most of your energy is deposited. So most of the photons are produced.
Super. I'm sure he'll be okay with the answer. Let's see. Then there's a question by Nicolas. Oh, but he is asking the same thing I did before. And he says that anyway, he would like to know how many neutrinos were expected from that. Sorry, I gave incomplete information. No, so from the neutron star merger. From the neutron star merger. He was asking that anyway, how many neutrinos were expected.
Oh yeah, now I would need to recall the numbers exactly. Unfortunately, I don't. So as I said, in the 500-second window, we actually did not expect to see any neutrinos. But if you're talking about how many you would expect from the merger itself, I mean, that strongly depends on the model, on the size, the distance. I mean, there's so many model parameters that we actually don't know all of them yet to make a precise statement of how many neutrinos we would expect from an event like that.
I see. Okay, let's see. So Herman is thanking you for your answer. Then Roberto is asking a question, but I think that you just did, right?
Yeah, was that the one that I asked?
Right? Yes, okay. And okay, that's about it. Farinaldo is sending his regards. Farinaldo Queiroz is sending his regards, specifically to Germán, Roberto, and Nicolás. So everybody else should be offended. Okay, any other question from the audience here?
Yeah, I have one more question. Nancy, what is the future of IceCube? I mean, is there a plan for an upgrade, I don't know, to make even more compact array of detector, or to combine with other techniques to
Yes.
improve the
Oh,
sensitivity of
there's several things planned. None has been approved yet, so we don't have money for any of those yet. But there's we are going in all directions. So we are planning for a high energy extension, so making IceCube bigger. That is what we call IceCube Gen 2. Basically, it would just mean that we put more strings out, and so IceCube would be basically the infill array of a much larger array, and by that we hope to find many more beyond PeV neutrinos. So probing the GCK regime as well. But then we also have, which I didn't talk about at all, a plan for a low energy extension. So there we are talking about the regime of neutrino oscillations, neutrino mass measurement via the mass hierarchy, and stereoneutrinos and things like that. So there we are planning for a much denser array that's looking at much lower energies, going down to a few GeV in energy. So here we were talking about 100 TeV, tens to hundreds of TeV. So there's these two frontiers, and basically as a compromise for the intermediate future, we are planning what is called Gen 2 phase 1, which is a few additional strings which carry several calibration devices, because now we are in a regime where we are not statistically limited anymore in many of our analyses, but we are actually systematics limited. And so we are limited for once about the knowledge of the ice properties. And for that, we want to deploy a plethora of calibration devices that help us understand the properties of the ice. And that would benefit of course, the upcoming extensions, but it would also benefit our old analysis, because we could basically redo the old analyses using the additional information about the ice. So we could improve on that a bit. So that is basically the intermediate plan to show feasibility of the upcoming improvements, and at the same time improve with the already existing data.
Okay, so in principle, with all these upgrades or that are planned, IceCube could last 3 more decades taking data. Or I mean, not infinite, but let's say.
It's actually pretty amazing. I mean, we have these 5,200 modules in there, and we expected to have, I don't know, like 1% or 2% dying per year, but we only really lost sensors in the beginning during the freeze-in. So when everything was still moving in the ice, so some connectors broke and things like that. But we only lost very small number, and basically since then we have not lost any of the modules, or only a handful of modules. So this gives us hope that actually the detector can be running for many more years. So. That was a very nice surprise.
It's a long-lasting experiment.
Yes. I mean, everything is static, so as long as nothing breaks, as nothing internally breaks, it can be very stable.
Okay, thank you.
Okay, super. So any last questions before we close the webinar? Okay, I think we're good. So before saying goodbye, I'd like to remind everybody that, hang a second. Let me check if there's any other question at the YouTube chat. Okay, so that's empty. All right. So before we finish, let me remind you that we have an upcoming webinar. We're going to be having Anirban Das talking about dark matter scattering on webinar number 53. Okay, so I hope to see you all there. Thank you again, Nancy, for the very nice talk, and we'll see you next time.
Thank you very much.
See you around, everybody.